Hi, my name is Ira Globus-Harris, and I'll be presenting my work with Michael Kearns and Aaron Roth on algorithmic frameworks for bias bounties. This work was done at the University of Pennsylvania and during an internship with Amazon Web Services. Any views and opinions are my own. Machine learning models discriminate in undesirable ways, and the study of algorithmic fairness is one attempt to partially remedy these issues. However, the field has several challenges. The most basic question is, of course, should we be doing this at all? This is an important question, and in many cases, I think the answer is no. However, I do posit that there are some cases where machine learning is a useful thing, and therefore tackling fairness with some sort of algorithmic approach maybe makes sense. I'm going to assume so for the rest of this talk. Fundamentally, algorithmic fairness is stated as a constraint to an optimization problem, where fairness is positioned in direct tension to overall model accuracy. Thus, in order to make a model fair, some groups' error rates will be artificially inflated. This is a hard sell to any organization whose goal is to market high accuracy machine learning models. Second, all downstream use cases need to be accounted for. The groups that you want to be protected against must be known ahead of time and fully specified, which we've seen in cases like the Twitter image cropping issues is not always the case. Furthermore, your fairness guarantees are only with respect to your training distribution. Your large model that's trained on well-lit centered images may not work well for a customer whose use case is primarily dimly lit images, but nothing about these guarantees would be violated. In an era where machine learning is a service, you want to be able to guarantee fairness in these new settings with minimal additional computational work, right? We don't want to have to retrain everything in all of these settings, just given, say, the environmental impact of a machine learning model. Then finally, there are no good mechanisms to improve unfairness discovered after deployment, right? There aren't good ways for a tech company to incorporate the new knowledge that external audits bring without completely retraining their model. And so the relationship between auditors and organizations is something that's adversarial instead of one that rewards auditors for their efforts and which makes the models better. So we'd like to have a form of algorithmic fairness that addresses these limitations. One that provides some notion of fairness without accuracy loss, that lets fairness concerns be addressed as they are discovered, which generalizes to new settings, and which has a constructive relationship between auditors and model owners. In this work, we tackle 3 of these issues. We're going to do so by looking to the security community, who have designed bug bounties. These programs turn a potentially adversarial relationship between software developers and hackers into a mutually beneficial one. Developers post bounties for security bugs in their software, and then they monetarily reward hackers who locate bugs. Here, we can imagine a similar bias bounties approach. So external auditors are invited to find bias in a model. They can send this information to the company. They're rewarded for doing so. And then their discoveries are incorporated into the machine learning model to create a better and more just one. We've seen such bias bounties events already beginning to occur in practice, such as with Twitter's Algorithmic Bias Bounty Challenge in 2021. However, algorithmic frameworks or more systematic approaches have not been considered. And such a model leads to some natural questions. For example, how should the bounty hunters describe the unfairness that they discover? How do we evaluate these descriptions? How do we distinguish between a case where the bounty hunter is describing a group that our model is expected to perform poorly on, such as the set of all very blurry images, or the set of all points in our training data that we misclassified, which of course we already know about, versus a group that really represents some real harms to some community? How do we incorporate this new knowledge into our model without completely retraining? How do we prevent adversarial behavior by bounty hunters who, for example, might try to learn our validation method and overfit to it just to get that monetary reward? Our work provides methods to tackle these questions. So we require that bounty hunters submit pairs of group identification functions G and models H, such that the model H does better on points in G than our current model F does. We then use holdout data to validate that this is in fact true, and we update our model to use the new model H whenever a point is in group G. So this is admittedly a lot of work for the bounty hunter. They need to have a general description of group G, and they need to have found a model that works better for it. But without this criterion, it isn't clear how to distinguish between groups we should expect to do better on and those that are inherently hard, such as the blurry images example. In essence, our model updates just form like a decision list, right? So after T rounds of updates, we have a decision list where point X will be classified according to the most recent group in the model that it is a member of. And this has a nice property. So if at each update, you encourage some sort of delta improvement over some mu density of your distribution, you will converge to close to the best possible model after 1 over mu times delta rounds of improvements. So that's not very many. This algorithm also has a problem, right? So if your groups overlap, which we know in the case of demographic identifiers will often be the case, you could have group errors increase over the course of updates rather than decrease. For instance, if the second bounty hunter finds group G2, which is African American women, and then a future bounty hunter proposes an improvement on group GT, which is all women, it could be that the second improvement is beneficial to women overall, but it does worse on the subset of African American women. And of course, we don't want this to happen. So what we do is we test for these occurrences. Whenever we make an update, we test to see if any group is performing worse than it was before. And in that case, we add a repair that diverts the group in question to the place where it achieved its best error. Call these pointer decision lists. And this final algorithm has the same convergence guarantees that to the best possible model as before, but it has the added benefit of monotonically decreasing errors for all groups over time. Finally, we use a validation process to check whether or not any of these updates are valid. This uses a holdout data set, and because we guarantee that we have a finite number of improvements until we can't find any more, we're able to leverage results from adaptive data analysis to guarantee that an adversarial bounty hunter will not be able to overfit to this holdout data set. Right? They won't be able to learn so much about it that they can just overfit to it and then get the rewards without really having a good generalizable result. One natural question is maybe, well, can we generate algorithmic methods to do some of this work that the bounty hunters do? So instead of crowdsourcing these GH pairs from the community, one could instead develop an algorithm that finds these areas of improvement by itself. And in some cases, this might not make a lot of sense, but at least it might be a good preliminary way of identifying sources of unfairness in a model pre-deployment or before turning the model over to a community of auditors. And in this work, we provide 2 algorithmic methods of finding these GH pairs. One reduces the problem to a cost-sensitive classification problem to identify these promising GH pairs. And the other considers the case where we have some well-defined class of G's and H's that we want to find the optimal pair in. And it plays an alternating maximization game between G and H. And it turns out that this just reduces to solving a standard empirical risk minimization problem. So in summary, our work provides an algorithmic framework for bias bounties that aligns the standard accuracy fairness trade-offs. It guarantees convergence to the best model and guarantees that group errors monotonically decrease over time. It provides a validation framework for the bounty hunter's submissions that prevents adversarial behavior. And finally, we provide an algorithmic method to identify groups and improvements that can automate the role of bounty hunters in preliminary efforts to identify and ameliorate sources of unfairness pre-deployment. So that being said, there are also several limitations to this work, right? So first of all, this validation process is over the training data. So we don't have a good way of verifying claims relating to the training data being misrepresentative. This is a general problem with fairness or algorithmic fairness, right? So for instance, if your model performs really poorly over trans people, but your training data doesn't have any trans folks in it, then a proposed GH update by auditors, where G is the group of trans folks, will just never be accepted, because even if their model does in fact improve on trans folks, because we can't validate that, because that group is not represented in the training data. And one possible workaround for this would be, in an ideal process, bounty hunters could send new training data to be incorporated into our training data, right? So, you're right. So they're sent the original training data. They say, hey, this training data is misrepresentative. Here's some new training data that I collected in my work, and maybe can you please incorporate that? And then we could reward them. But in order to do this, we need to be able to do two things. We need to know how to weight that new data, like what portion of our distribution should be the new data, and also how do we validate it? How do we know that this data is good data? And this is going to be particularly a problem in contexts where like downstream use cases may have substantially different distributions than training data. But we don't know how to validate, so it's unclear really how to proceed in these contexts. Another issue is we're asking a lot of our bounty hunters, right? In the original problem statement, we thought, okay, we're giving people the model F, and then they're just going to send back some sort of description of unfairness. Maybe, you know, hey, it performed badly on me and people like me, and then we could fix that and we could give them this monetary reward. But in many instances, right, so what we've actually ended up asking is for people to provide both a group G, which is like a generalizable function that given a point X tells you if it's in the group or not, and a model H that does better than F on G. So that requires some like real machine learning knowledge to come up with these G's and H's. And in many instances of unfairness in deployed models, it isn't experts in the machine learning community who are identifying problems. Instead, it's impacted users who may not have the technical ability to generate these pairs. So in order to resolve this mismatch between what we need to require from a bounty hunter just for the process to have a reasonable guarantees and this accessibility issue, one thing we can do is we can imagine an interface that converts these descriptions of unfairness by the community into these GH pairs that we actually need. So last semester, we ran a pilot version of a biased bounties program over census data from the folk tables data set in UPenn's ethical algorithms design classroom. And this class had students from a very wide variety of backgrounds, some of which had very little coding experience. And we included a very nominal version of such an interface. And it did allow students to identify some improvements to the model that they were given. But this was particularly straightforward in this context because census data is nice and tabular, right? You can look at it, you can classify things like race, income level, sex, disability status, just based on the different features of the data. And it's a lot less clear how to make such a straightforward interface for problems with more complex or opaque feature spaces, such as in image classification or audio transcription tasks. And in these cases, a function G that identifies group membership is going to be much more complex potentially. And even just requiring community members to say label membership in a group in order to generate such a model that could identify these group members may be an extremely arduous task. So it's not really clear how to do this in these more complex settings in a way that's very accessible. And it's not clear how to do this in cases where the training data is misrepresentative. And I look forward to hearing other folks' ideas about how to resolve these issues. Thank you very much.